On paper, the Rathoahariam Bridge is impressive. Its total length is approximately 3 kilometers, making it a substantial piece of infrastructure rather than an ordinary local crossing. The approach roads were designed to connect it into the surrounding road network, while the bridge itself was intended to create a much shorter route across. The Golden Gate Bridge is one of the most photographed structures on Earth, a 2.7-kilometer line of steel that appears to float above San Francisco Bay. But imagine seeing another bridge that had already consumed years of work, with most of its structure standing, while the final connection remained missing and the construction site simply stopped. Engineers didn't abandon the laws of physics. The project became trapped in contracts, funding, land access, and coordination problems. This is the Rathoahariam Bridge. And here's what nobody tells you about how a bridge can be almost finished, yet remain unfinished for years. The Rathoahariam Bridge was conceived as part of the infrastructure around Mangla Dam, with a straightforward public purpose: connect communities around the reservoir and dramatically reduce travel between Mirpur, Islamgarh, Chakswari, and surrounding areas. The project was initiated in 2011, and the approach roads were eventually completed, but the bridge itself became a different kind of engineering story. The client was the government, working through public sector infrastructure arrangements in Azad Jammu and Kashmir, while the project became tied to the wider Mangla Dam raising program. The brief sounded simple enough. Build a major crossing over the reservoir and connect the communities that had been separated by the expanded body of water. But the scale was not simple. The bridge is roughly 3 kilometers long. And according to officials, by the time construction stalled, about 80% of the work had already been completed. Think about that for a moment. Happens when a mega project reaches the final few percent and discovers that the final few percent may be the hardest part. Reservoir. For residents, the benefit was obvious. A completed crossing could cut travel times between communities on opposite sides of the reservoir and provide a direct connection toward Mirpur and other major towns. Officials also described the finished bridge as having the potential to become a significant tourist attraction because of its location across the vast waters of Mangla. The numbers tell another part of the story. The project was initially estimated at around 1.3 billion Pakistani rupees. Years later, the reported cost had risen beyond 9 billion rupees, with the government eventually approving another 5.5 billion rupees for completion. That is a remarkable escalation. But that is not the remarkable part. The remarkable part is that around 80% of the bridge could be complete while the project remained functionally incomplete. And then the engineers started doing the math. Here's the thing about a bridge over a reservoir that every civil engineer knows. The water isn't just scenery. It is part of the engineering problem. A normal road bridge crosses a fixed landscape. Its foundations are designed around known ground conditions, predictable access, and a relatively stable relationship between the structure and the land. The moment you build across a reservoir created by a major dam, everything changes. Water levels rise and fall. Construction access changes. Foundations have to be placed in difficult ground. The structure has to deal with environmental exposure, fluctuating water conditions, and the enormous challenge of constructing a final span where the geometry of the entire bridge has to come together precisely. Let's talk about what happens structurally when you leave a major bridge unfinished. A bridge isn't simply a collection of independent pieces. Loads move through the structure from the deck into beams, from beams into piers, and from piers into foundations. The technical term is load path, meaning the continuous route through which weight and forces travel safely into the ground. Break that path, and you don't have a complete bridge. The Rathoahariam project became stuck around its central span, reported at approximately 160 meters. That meant the bridge could be largely built without actually performing its primary function. Not slightly. Not as a design flourish. The connection was missing. This is where the project became technically unusual. The challenge wasn't simply pouring more concrete. Officials later described work involving foundations in marshy ground and the use of German-made machinery to excavate and construct the remaining sections under changing water conditions. The final 125 meters were reportedly planned using a balanced bridge construction system designed to manage the conditions around the reservoir and reduce dependence on temporary support in the water. That approach matters. In balanced construction, engineers build outward from supporting piers in controlled stages, keeping the structure balanced as the span grows. It is a method used on major bridges precisely because placing conventional temporary supports in deep or difficult water can be expensive and technically complicated. The problem was that the bridge had already become a project with several moving parts. Funding, legal issues, administrative decisions, technical constraints, and changing water levels. In 2024, officials and residents described the bridge as having been stalled because the 160-meter central span had not been constructed. The project had effectively reached the point where the missing section controlled the fate of everything that had already been built. But here's something about this building that nobody ever explains. Except it isn't a building. It's a bridge, and that distinction matters. The public sees concrete piers, steel, road surfaces, and a structure stretching across water. Engineers see a system that has to remain aligned to millimeters across enormous distances. One secondary complication is access. Construction equipment has to reach the work zone, and when the work zone is surrounded by reservoir water or marshy ground, ordinary construction logistics become complicated very quickly. Another is water level. The bridge's remaining work has been connected to periods when reservoir levels are low enough to make certain foundation and piling operations more practical. That means the construction schedule isn't controlled only by workers and machinery. The environment becomes part of the timetable. And this part barely gets mentioned anywhere. The bridge also has to connect to roads that already exist. A completed span that doesn't properly integrate with its approaches is not a functioning transport link. The approaches, ramps, drainage, pavement, safety barriers, and road geometry all have to work together. Infrastructure is rarely defeated by one dramatic problem. More often, it gets trapped by dozens of ordinary ones. That part doesn't make it into the architecture magazines. And then there is the most human complication of all. People waited. By 2020, public discussion around the project described it as having been under construction for years, with the work reportedly stopped around 2016. Residents saw the structure sitting across the landscape while the promised connection remained absent. No dramatic collapse. No spectacular engineering failure. Just time. Within 1 year, the bridge was still incomplete. Within 4 years, the same unfinished connection had become part of the project's identity. The structure wasn't failing in some cinematic way. The problem was that it wasn't doing what it had been built to do. Nobody was hurt in a bridge collapse because there wasn't one. The incident was the absence of an ending. And that may be harder to explain. Compare this with other major bridges. The Tacoma Narrows Bridge famously failed through aerodynamic instability in 1940, teaching engineers how wind-induced oscillation can destroy a structure. The Millennium Bridge in London survived its opening day, but unexpected lateral movement caused engineers to close it temporarily and retrofit dampers. The Akashi Kaikyo Bridge in Japan survived the 1995 Kobe earthquake and remains one of the world's longest suspension bridges. Different problems. Different outcomes. Here is the fundamental difference between the Rathoa-Hariam Bridge and every other major bridge we've covered. Its defining problem wasn't that the completed structure failed. It was that the project never reached completion in the first place. And now comes the uncomfortable part. A bridge that sits unfinished for years creates a very different engineering question from a bridge that has been operating for decades. Materials age. Concrete undergoes creep, meaning it slowly deforms under sustained load. Steel can corrode when protective systems deteriorate. Bearings can wear. Expansion joints can fail. Water can enter tiny cracks and reach reinforcement. But here's the question that sits beneath all of this. What happens when a major structure spends years in an incomplete state before the final system is connected? The honest answer is that every component still has to be assessed according to its actual condition. There is no single number that says an unfinished bridge becomes unsafe after 4 years. There is no universal countdown clock. The engineers have to inspect the concrete, reinforcement, foundations, bearings, joints, exposed steel, and alignment before deciding how the remaining work should proceed. And that is where the absence of data argument becomes important. There is no historical data for what a Rathoa-Harriam scale bridge looks like after 4 years. There is no universal countdown clock. The engineers have to inspect the concrete, reinforcement, foundations, bearings, joints, exposed steel, and alignment before deciding how the remaining work should proceed. And that is where the absence of data argument becomes important. There is no historical data for what a Rathoa-Harriam scale bridge looks like after spending many years incomplete, because no identical project has followed exactly the same construction history. This is the first. It is the only one. By 2030, engineers will be looking at inspection records that today's project teams cannot yet have. By 2040, another generation of engineers may be reading those records to understand how long-term exposure affected the structure before completion. And honestly, that's a little unsettling. Not because the bridge is destined to fail. There is no evidence for that. The unsettling part is simply that infrastructure can outlive the people who made the decisions that shaped it. A project manager who saw the bridge in 2015 may be retired by 2030. An engineer who inspected one of its piers may no longer be involved when the next major assessment happens. The structure remains. The paperwork remains. The data remains. Hopefully. But here's the detail nobody surfaces. The bridge was never just a construction project for the people living around it. For them, it was supposed to change ordinary life. A shorter journey. A faster trip to work. A simpler route to school. A connection to another town. You can picture the small details that make infrastructure meaningful: a motorbike carrying 2 people along a dusty road, the smell of hot asphalt in summer, a driver watching the reservoir through a windscreen while taking a route that exists only because another route never opened. People don't experience a bridge as a structural diagram. They experience it in minutes. 20 minutes saved. An hour lost. A road avoided. A journey made possible. None of them are thinking about the load path. They're thinking about getting home. And right now, somewhere around Mangla Reservoir, the idea behind the Rathoa-Harriam Bridge still exists in concrete, steel, unfinished connections, and a public expectation that began more than a decade ago. A person can stand near that enormous structure today and see what was achieved. And what wasn't. The question is no longer whether engineers know how to build the final span. The question is what years of delay have changed before that final connection is made. Drop it below. Would you trust a bridge that spent years unfinished before opening to traffic? See you in the next one. Verify. Rathoa-Harriam Bridge project in Azad, Jammu and Kashmir, Pakistan. Mangla Dam, reservoir and dam associated with the project. Project initiated in 2011, reported by Pakistani news coverage. Approximately 3 kilometers, reported length of the Rathoa-Harriam Bridge. Approximately 80% completed before the central span, reported by officials and residents. 160-meter central span, reported as the missing section that stalled completion. Approximately 4 kilometers of approach roads, reported as completed. Initial estimated project cost, approximately PKR 1.3 billion. Reported later project cost, more than PKR 9 billion. Additional approved funding, approximately PKR 5.5 billion. German-made machinery, reported for construction work in difficult, marshy ground. Final remaining construction section, approximately 125 meters, reported in connection with the planned balanced bridge construction system. Project stalled around 2016, reported in public discussion and later news coverage. 2011, project initiation date reported in Pakistani media. 2020, public discussion documented the bridge as having remained stalled for several years. 2024, reports described renewed efforts and the removal of legal, technical, administrative, and financial obstacles. 2030 and 2040, future years used as illustrative projections for possible engineering inspection records, not documented project deadlines. Load path, engineering term describing the route through which structural loads are transferred through a structure to its foundations. Creep, gradual deformation of concrete under sustained load. Tacoma Narrows Bridge, suspension bridge that collapsed in 1940 due to wind-induced aerodynamic instability. Millennium Bridge, London, pedestrian bridge temporarily closed after unexpected lateral movement following its 2000 opening and later retrofitted with dampers. Akashi Kaikyo Bridge, Japan, major suspension bridge that survived the 1995 Kobe earthquake and remains a record-setting long-span bridge. No evidence was found in the cited sources indicating that the Rathoa-Hariam Bridge itself has suffered a structural collapse. No claim is made that the bridge is unsafe or likely to collapse. No deaths or injuries are attributed to a structural failure of the Rathoa-Hariam Bridge.